Hi, welcome to the 3.1 Stoichiometry Intro to Stoichiometry notes video. At this point, you should have most of the notes done. I'm just going to walk through what we have not captured already on our notes. So if you need to, read over what you already have done. Now remember, stoichiometry is a process where you're converting from one substance, the amount of one substance, to another, and the only way you can do that when you change substances is they both must be in moles. So the key part to stoichiometry is using mole ratios to convert from one thing to another. There are two types of stoichiometry. There's compositional and reaction stoichiometry. In class, we have not covered compositional stoichiometry, but we do have an example here, which I will go through quickly. If that is confusing for you, you can go ahead and skip ahead in the video to where we get to the reaction examples below. So in compositional stoichiometry, we use subscripts in the chemical formula to convert from the amount of one thing to another. And the best thing to do is to look at an example. So here we have an example which says how many hydrogen atoms are there in 5 grams of water. So we know that water has 2 hydrogen atoms for 1 water molecule. And we can also say that there are 2 moles of hydrogen for 1 mole of water. And that's what we're going to use. But since our given is in 5 grams, we first must convert the 5 grams of water to moles of water. And our overall process will look like this. We'll go from 5 grams of water to moles of water, from moles of water to moles of hydrogen, and from moles of hydrogen to number of hydrogen atoms. And this is what the work would look like. So in our setup, we'll start with the 5 grams of water over our 1. Our given is always over 1. And in the second fraction, I have the conversion factor to convert from mass to moles, and that I use the molar mass of water. And I set it up so that the units, grams of water, cancel out, so they have to be opposite. The next fraction is the mole ratio, and since this is a compositional stoichiometry, what I'm using for the mole ratio are the subscripts. Since there are 2 hydrogen atoms for 1 water, that's where I'm getting these numbers from. So 2 moles of hydrogen atoms over 1 mole of water. And the last step is to convert from the moles of hydrogen atom to what they're asking for, which is number of atoms. So if I want to go from moles to number of atoms, we know from our mole map that we would use Avogadro's number. So I put 6.02 times 10 to the 23 atoms on top, and then the 1 mole, which is the mole of hydrogen, on the bottom, because we know that in 1 mole, it's Avogadro's number of atoms. Then to do the math, since you're multiplying fractions, you multiply straight across, so 5 times 2 times Avogadro's number, that's what I have in the numerator, divided by 18. And so when I multiply the numerator out, I get 6.02 times 10 to the 24, and then I'm going to divide that by 18.02, and then I get this number, 3.34 times 10 to the 23 hydrogen atoms. So that's some compositional stoichiometry. Let's go into reaction stoichiometry. With reaction stoichiometry, we use the coefficients in the balanced chemical equation as our mole ratio. So when you read a chemical reaction, you can read this reaction as 2 moles of hydrogen reacts with 1 mole of oxygen to make 2 moles of water. And it's kind of like a recipe. So that's the understanding that we use to solve a problem like this. So this first problem is a simple reaction stoichiometry. It's called a mole to mole. Because if you look at this problem where it says how many moles of O2 do you need to react with 0.798 moles of H2 in that same reaction that we looked at above, we can see that our given is in moles and our find is in moles. And so that makes the problem quite easy, because the only thing that we need to convert, since they're both now in moles, is just the mole ratio from the balanced chemical reaction equation. So this is what our setup would look like. Again, we would start with our given, 0.798 moles of H2. And in the second fraction, which is our conversion factor, we are going to arrange our find, which is our given, which is 2 moles of H2. So we're going to take that piece of the reaction, put it in the denominator, so that moles of H2 can cancel out. And then what we're asked to find, which is O2, and it has an invisible 1 here as a coefficient. So 1 mole of O2, that goes on the top. All right. So this information comes from our balanced chemical reaction equation. And then when we multiply the two fractions, we do 0.798 times 1, which is 0.798, divided by 1 times 2, which is 2. So you're just dividing 0.798 by 2, and you get this number. Now, you could probably solve this conceptually, because remember, when you're looking at these stoichiometry problems, what you're saying to yourself, using the mole ratio, this mole ratio is telling us that for every 2 moles of hydrogen, you need 1 mole of oxygen. So with that being said, if you have 0.798 moles of hydrogen, you're going to need half that amount of oxygen. And the dimensional analysis just allows us to solve that in a way where we're not really thinking so much if we're having to multiply or divide. We're letting the units decide that for us. All right, last example here is the mass-to-mass stoichiometry problem, and it's called mass-to-mass because in this case, our given is in grams. So it says how many grams of H2 do you need to make 5 grams of H2O according to that same reaction, and our find is in grams. So if you're going from mass to mass, you're going to have 2 additional steps. The first step is to convert your given into moles, and then your last additional step will be to convert the moles of H2 once you solve for it into grams. So let's see what that little setup looks like. So we're going to go from grams of water to moles of water to moles of H2, and then to grams of H2. So in this case, we need 4 fractions that we're going to multiply. The first fraction always has our given, 5 grams of H2O. Second fraction, I have the conversion factor to go from grams to moles, and that I use the molar mass of water, which is the 18.02. Notice that the 18.02 goes in the denominator so that the grams of water are opposite so they can cancel out. Now that I have moles of H2, I can convert to moles of moles of H2O, I can convert to moles of H2, and these numbers come from the balanced chemical reaction equation. My given is 2 moles of H2O, so that goes in the denominator so that the moles of H2O can cancel out. And then my find is H2, so I put the 2 H2 on top so that can cancel out. And so you can see it's a 2 to 2 or 1 to 1 ratio. So technically, whatever the moles of water that you have, that's the same number of moles of H2 you're going to have. All right, if I were to stop here, I would just have the moles of H2, but I need to get the mass of H2. So for that to go from moles to mass, we use the molar mass. 2.02, that should be grams. There we go, ahead and correct that. Grams of H2 goes on top, and then the 1 mole of H2 go on the bottom. This is from the molar mass, so that way my moles of H2 can cancel out, right, which they've canceled out. And then the math looks like this: 5 times 2 times 2.02 in the numerator, divided by 18.02 times 2, and then I get 20.2 divided by 36.04, and that gives me the final answer. I hope you found this video helpful, and have a quality day.